So very good morning, and after the brief introduction, we'll start the workshop. And obviously, whenever you go to the war, you have to learn your instruments. So we will discuss about the technical aspects of the EEG recording. And whenever we discuss as a biologist and physiologist about the technical aspect and physics, everybody feels a bit uncomfortable. That this is probably the things we need not know about the technical aspect. We have to just see the reporting and report the EEG. And probably it is not our fault, and probably it is difficult also. So what we will be discussing in next 40 minutes, that what are the important practical aspects which as a clinician we should be knowing whenever we try to report and read the EEG, and how we can avoid the pitfalls by knowing these technical aspects. So this is, sir has already mentioned about the book, and we will be discussing about from the first chapter about the technical aspects of this. So starting with how the EEG waveforms are produced or how they are generated. So this is a simple physiology. If you look into it, in the pyramidal cells in the superficial layers of the cortex, these pyramidal cells are located in these vertical columns. And each pyramidal cell has one axon and one apical dendrite. And on the superficial surface of this dendrite, apical dendrite, there is axonodendritic connections or synapses. So whenever there is a action potential which is generated in the neuron, and this action potential through the axonodendritic connection goes to this synapse. So if it is an excitatory synapse, there is a release of the glutamate leading to the opening of the sodium-potassium channel on the postsynaptic membrane over the dendrite. And whenever there is a sodium-potassium channel opens, from the first year of MBBS, we have read that sodium ions goes inside. So effectively, positive ions goes inside. So what happens that there is a negativity in the extracellular space. So in the superficial layer over here, there will be a negative potential. In the deeper layer here, there is a positive potential. So what you get is basically a charge or a dipole, like a battery. We have a cell or battery where one hand has a negative and one hand is positive, which produces this charge. And these dipoles from a large group of neurons, which is resulting from the either excitatory or inhibitory postsynaptic potential, these produce the EEG waveforms. So EEG waveforms are not produced by the action potentials. Action potentials are very short duration and very small, and these are not detected on the surface. So this excitatory extracellular potential resulting from these excitatory postsynaptic potentials, they produce the EEG signals. Now, whenever there is excitatory postsynaptic potential, and there is a negative end is toward the surface, and negative end produces, as upward deflection in the physiology, negative is up. So this will produce a upward deflection on the EEG waveform. If there is an inhibitory postsynaptic potential, that will produce a downward deflection. Fortunately, more than 95% of the synapses are excitatory synapses. So majority of the time, whatever we get in the EEG are upward deflection or upward looking waveforms. So this is how the EEG waveforms are produced. And we understand there is a potential which is produced from the one single axon or one single cell will be very small to be detected. So there is a large number of dipole sheets or large number of dipoles from a group of neurons which are firing together, that will produce a EEG signal, normal EEG signal. In case of epilepsy, what happens that epilepsy is a state of hypersynchrony. So there is a hypersynchronous discharge of a large group of neurons. And that is why the deflection which will be produced by this hypersynchronous discharge will be large. So that is how the spike will be generated in the cases of epilepsy. So this is the process of generating the spike. This is known as the paroxysmal depolarization shift, because of the increased excitability as well as the increased hypersynchronization. And what we look into the EEG waveform, these are the EEG waveform which we finally look onto initially in the analog EEG and now in the digital EEG. So one thing we need to understand that these EEG waveforms or EEG signals which are produced, Basically, what we do while reading the EEG, that we have a EEG waveform, or let us say this spike on the left temporal lobe. And based upon this location, we deduct that this spike is coming from the temporal lobe. Now, we have to understand that this spike, which is on the surface on the left temporal lobe, can be produced from the source, maybe the multiple. It may coming from the left temporal, from the lateral temporal, from the insula, from the even from the basifrontal lobe. So that EEG has a poor spatial localization. That is, a left temporal spike doesn't mean that it is coming from the temporal lobe. And that we need to understand when we're reading the EEG. So EEG has a good temporal resolution, manifestation within the few milliseconds. But the resolution in the space is a bit low, and this limitation we need to understand while trying to interpret the EEG. So this is the one concept, physiological field, which we'll be discussing again and again throughout the workshop. And so what we mean by physiological field, as I told you, that it is the large group of neurons which fire together to produce the EEG signal. So it has been estimated that at least a 6 square centimeter of the brain area should be activated before that signal is detected by the EEG electrode on the scalp. So you understand 6 square centimeter means it will cover the more than one electrode. So any activity which is coming from the brain, it will be at least will be covering a 6 square centimeter area, and it will be detected in more than one electrode. The electrode which is lying just above the source will show the largest activity. The nearby electrode also will show the activity, but with a smaller amplitude. So the electrode which is lying just above the source is showing the largest amplitude of activity. As you move away from the source, the other electrode also show the activity, but of a gradual lesser amplitude. So it's a gradual decline in the amplitude as you move away from the source. So one thing, that activity which is arising from the brain will never be confined to the one electrode or one channel. So in other words, any activity which is, if you see in only one electrode, is not of cerebral origin, it is likely that it is an artifact. That is the one concept. And that is that each field, you mean that whenever any electrical activity, it will show from the maximum in the one electrode, so we can localize that probably this is activity is near to this underlying electrode or electrode. So that is the source of that. And the nearby electrode also will show activity which of a gradually tapering or gradually decreasing amplitude. So this is what we understand by the physiological field, and this is very important whenever we try to identify and localize the epileptiform activity, spike or sharp wave. So the spike should have a physiological field, and the activity which is maximum in one particular electrode, we usually indicate that this is the source. So this is the simplest model of the EEG machine, and EEG machine is nothing but it is an amplifier. So it amplifies the small activity which is generated into the brain. This activity is amplified by thousands of times. The nanovolt activity amplified to the microvolt, and then subsequently it is detected on the scalp. So we have this electrode, silver clad electrode, which are connected through leads to this differential amplifier. We'll see what this differential amplifier means. Then there are analog filters. So there is a hardware filter within the EEG machine which filters the activity. Then subsequently this activity is again amplified. In the case of digital machine, this analog signal, this is a hard signal which is converted to a digital signal by analog digital converter, which is a core of the digital machines. It is stored on the computer, and when we try to review the EEG, this digital signal is again converted to analog signal on the computer screen, and that is how we see the EEG. So that is the simple model of the EEG machine. What we understand by the differential amplifier, that if you put one electrode, let us say anywhere on the scalp, and connect it to the amplifier, what will be recording? So that what will be recording is a lot of noise, because the activity from the brain is of small amplitude. The surrounding atmosphere, his electrical activity in the atmosphere is too large. and that is why it will be overriding the EEG activity. So we need to remove that activity or external noise. So how we can remove it? So that is the way how we do it. So that is a differential amplifier. So what we do is we connect two input 1 and input 2, or one electrode 1 and electrode 2 to this amplifier. And what does this differential amplifier does? It removes the common activity. So there is an external noise which is common to both the input will be removed, and the difference of this activity, difference will be amplified. So this common activity is this noise which is common to both the input. So this activity will be removed, and only the EEG activity or the activity of the brain will be amplified. So this amplifies the difference between the two inputs and removes the common activity. So this is also known as the common mode rejection amplifier or a differential amplifier. Amplifies the difference and removes the common activity so that you get the activity from the brain. This was the older analog EEG, paper EEG, how the EEG machines were, you may see in many of the older departments. But now this has been replaced by the digital EEG. So basic concept of digital EEG is similar to a music CD or music DVD, where the music is stored in a mathematical formula, and when you put this CD into a CD driver or computer, you hear the music. So similarly, here these analog signals are sampled and stored as a mathematical values or as a digital values, and when we want to see it, these mathematical signals or digital signals are reformatted and again can be as waveforms, and we see on the EEG computer. This is possible because all the recordings, and one of the importance of this digital is recordings are obtained, as I told you, because we have to obtain the recording in the reference to another electrode. So there has to be two input when any channel or in the EEG amplifier. So in this recording are obtained to a common reference electrode. So we have a common reference electrode which is placed in between this ground and between the FZ. And this is known as the system reference electrode. And this system, all these electrodes, whenever we initial recording, there is a machine, all other electrodes are referenced to this reference. And then subsequently, we can subtract from each other and reformat the montage. So how it is done? So this FV1 is also reference to the system reference. F3 is also reference to the system reference. So suppose we want to have a FV1, F3 channel, then you just subtract this activity from this system reference is common. So finally, if you subtract this, we can get this FV1, F3 channel. And similarly, all the other channels can be reformatted. This is just to make you understand how this is done. Okay, this computer does it within a blink of the second, with all thing is taken care of. You change to the bipolar montage and you have these all different channels. But this is how the process, and this is why if your system reference is not properly placed, all of the channels will have an artifact or will look abnormal. So if you have a EEG which is showing that all the electrodes are not working properly or all the channels, then it is likely that there is a problem in the system reference. Another important concept of EEG machine which we have to understand when buying this machine is the sampling rate, because these analog signals has to be sampled at a particular frequency to convert into a digital signal. So this is a physics, suppose, and this is how these sinusoidal waveforms are sampled. So you have this sinusoidal waveform. This is analog waveform. Suppose it is sampled at this frequency of 1 hertz. So there is in 1 second, only one sample. So you will have a sampling here, here, and here. So finally, when you reconvert it, the computer will connect only these dots, and you will get a straight line. So your original signal is like this, sinusoidal, but when you have a low sampling rate, you will get a straight line. So your sampling rate should be sufficiently high that your original waveform is reproduced in as best possible as way. So you can see if your sampling rate is frequent, that is maybe around 50 hertz per second, so in a 1 second, 200 or 250 samples, then it can be exactly reproduced. So this is how so I will skip this. So this is if you suppose you have a sampling rate of 50 hertz, then your original EEG waveform, this will look like this. This will be like deformed waveform like this. So it has been calculated that your sampling rate of the machine should be twice the frequency, which highest frequency which you are going to record. So in EEG, in the scalp, highest frequency we tend to record is 100 hertz. So its EEG machine sampling rate at least should be 200 hertz. So all the commercially available EEG machine have a sampling rate of around 240 hertz. So this is the minimum sampling rate which is required. Now, sampling rate, your supplier, this is very commonly I have seen, sampling rate which the supplier gives to you, they will tell you 240 hertz. But when they install the machine, they will set the sampling rate as a lower side. So what will happen that if your sampling rate is low, your all artifact and this will become smooth. So when they are trying to sell you the EEG, they say that, oh, their EEG waveforms are very good and there are no artifact and it is recording very properly. And this is a very common scenario because many of the neurologists don't understand about that. So this is that sampling rate when you ask for the machine, and same when they set the machine, sampling rate should not be modified when the machine is installed. So that is the important thing which we need to keep in mind. Another is resolution of the machine. This resolution is of the screen resolution. If you see your EEG on a screen, and if you change the resolution of your panel or your screen resolution, you will say that you can yourself and see that EEG waveforms are deformed. So in the EEG machine or the old digital machine, resolution should be at least 16 to 24 bits. But in cases of these computers and these, usually you see the highest value, 1640 into 728 or 820. So that is the screen resolution. So we try to keep the highest resolution for that EEG machine while we're reviewing the EEG. So now coming to the electrode placement, and all of you know that we have this 10-20 system of electrode placement. You require a uniform system of electrode placement so that the same, you can compare the record between the patient, in the same patient at a different time or across the centers. So you have to have and then you have to account for the different head size, small head size versus a bigger head size. So the smaller head size T4 should correspond to a bigger head size T4 also. Okay, so for that this standard system has been developed. So according to the size of the head, we need to place these electrodes. And this is the 10-20 system of electrode placement where we have a 19 electrode, 2 reference electrode A1 and A2 and 1 ground electrode. Conventionally, odd number are this, and each electrode has 2 numbers. In the prefix indicates the location, suffix indicates the site and the location. So we have this frontopolar, frontal, and left-sided electrodes are by conventional named as the odd numbers, right-sided electrodes are even numbers. So this is the standard, I think majority of you will know it. And this is known as the 10-20 system electrode because electrodes are placed at a particular 10% and 20% of the major differences. 2 broad lines are, one is the line which is drawn from the nasion to inion, and another is from one preauricular point to the another preauricular point in the coronal plane. On the sagittal plane, suppose you have a 10 centimeter of this distance. So around 10% of this, so at a 1 centimeter you will put FVZ electrode, that is FVZ. Then 20% of that next distance is FZ electrode, and next 20% is CZ. So this is how you calculate the difference, put at 10 and 20% of the distances, and that is why it is known as the 10-20 system of the electrode placement. I will not go into the detail of placement. It is convenient and easy to use and provide comprehensive information in majority of the recordings. But because the number of electrodes are less, so the inter-electrode difference is almost 4 centimeter. So for any activity between the 2 electrodes, sometimes we may not be able to localize precisely. And for that precise localization, probably you can do is increase the number of electrode. People have developed this 10-10 system and 10-5 system, well 5% or 10% of difference. But you understand this is a 74 electrode. And if your technician is going to put 74 electrodes, then probably you will be able to do only 1 or 2 EEG in a day. So for that is why for the majority of the routine scalp EEG, 10-20 system of electrode placement is sufficient. In few selected cases of pre-surgical evaluation, we can use this modified 10-10 system where suppose you have a source here, then we can put some additional electrode in that particular area to better localization. So that is how the different systems can be used. So as I told you, there is each amplifier, or we have to have two input to record the EEG. So the potential, or this between these two inputs or these electrodes, so the difference between these two electrodes, this voltage fluctuation, so this is as a forms a one channel. So channel is voltage fluctuation between a single pair of electrode. So these are electrodes, and when you connect these to each other, so the difference of between these two is this channel. And when these channels are connected in a particular logical manner, in a particular sequence, it is known as the montage. So you can connect any electrode to any electrode in any sequence, and you will get the signal, isn't it? But what for the standardization purpose and for maintaining the uniformity, these systems or montages has been developed where there is a particular sequence of connecting these electrodes. So there is when we have a two input, when both the inputs are active, as in the ECG, that both the inputs are active, then it becomes the bipolar derivation. When the bipolar means both the poles or both the inputs are active. And this bipolar, in this bipolar derivation, we can connect this electrode in a different manner. So one way is that connecting this electrode longitudinally, so that Fe2 is connected to F4. Connected means the channel Fe to F4, which show a difference between the Fe2 and F4. And then F4 is connected to C4. So here F4 is input 2. In the next channel, it becomes the input 1. And in this sequence, these are connected in two chains. One is parasagittal chain, other is this temporal chain on the right side and left side. When it is seen from this profile, you look like two bananas. So it is also known as the double banana montage. It is the bipolar derivation where both the electrodes are active. Bipolar, within this bipolar derivation, electrodes are connected in a longitudinal manner. So it is a longitudinal bipolar montage. Okay, so similarly, we can connect the electrode in a transverse manner to each other, and this becomes still a bipolar derivation. Both the electrodes are active, but montage is bipolar transverse bipolar montage. Okay, so here what we will see is that in bipolar montage, your both inputs are active. So in this Fe to F4 channel, we will see the difference between these two inputs, but we will not show the absolute activity of that particular electrode or particular input. So to see that, or to measure the absolute activity, or what is the absolute potential as Fe2, your another input should be zero as possible, so that you subtract 0 from any signal, you will get that particular or absolute activity of that particular channel. So this is how this reference montage has been developed, where you connect these all electrodes to a particular reference electrode, which is believed to be inert, or which activity is believed to be 0. So in original 1020 system, this A1 and A2 electrodes were kept. So here, all these electrodes are connected to a common reference, which is A2 in this case, and this will be a difference between Fe2 and A2. So you can have different types of the references in the case of the referential montage. So this becomes a year reference montage. But then there are certain advantages and disadvantages of using the reference. There is no point in the body which is completely inert. So suppose we use A1 and A2, they are very near to the temporal lobe. So in the cases of temporal lobe epilepsy, A1 and A2 will not be 0 or will not be inert, they will also become active. And when as you know, when the reference become active or become contaminated, it is difficult to really judge that activity. Similarly, we can use the CZ central electrodes, but during the sleep, that will become active. So to overcome this problem, this concept of common average reference has been developed. Common average reference is not a point in the body, but you select a group of electrodes, and mathematically the computer devise a method, or computer calculates so that this activity becomes 0. So what happens that suppose you take 10 electrodes in that reference, and you combine the potential of all the 10 electrodes. So suppose, let us say, if electrode has a potential of 10, so you combine 10 means 10 plus about 10, so it becomes 100. Now you take mean of that, so that is again 10, and from that mean you subtract the individual electrodes, so 10 minus 10 becomes 0. So this is how the mathematically it is calculated. Computer does it for you. But this is a case of where you can have a potential of that particular common average reference to as 0 as possible. How these different montages work, I'll give you some example. This is a bipolar montage, left, right. If you look carefully, there is probably small spikes which you can see in the probably left temporal. You may not be very sure. There is some slowing on the left temporal, probably a spike. So this is in the bipolar montage. Now what will happen in the case of, suppose, in the referential or this is common average, you can immediately make out that one is that amplitude is higher and then its spike is more prominent. Why it is not visible here? Because what will happen that in this T1 and T3, because it is a difference. So if T1 is also negative and T3 is also negative, the difference between these two will be low. In average, what will happen that average is 0. So it will show the absolute potential F7 and T3. That is why the amplitudes are higher in the average montage, and sometimes localization becomes easy in the average montage. So in a case of doubt, always try to see in two montages and try to use two montages. And for practical purposes, if you use longitudinal bipolar montage and a common average montage, you will not need any other montage in your life. In last 25 years, I have never used any montage other than this. So you have to understand the utility of different montages, try to see whenever you face with a difficulty, and try to be familiar with these montages. So another example, you can see there is some activity or some slowing in the left temporal in the bipolar montage. But same activity if you see in the referential, you can make out there are the small spikes in the F3 and even in the CZ and PZ. Why this is not seen in the bipolar? You see that these are the same activity in FZ and CZ. So if you subtract CZ from the FZ, because of the same activity, 1 minus 1 is 0. So you will not get that activity in the bipolar montage. But it can be reflected here in the average montage. So this is the average montage definitely provides more information, but it is a difficult montage to use and requires some experience. So always initially see in bipolar montage, when you start reading the EEG, in cases of difficulty, you try to switch over to average montage. But gradually, over the last many years, I have now primary montage I see in the reference montage, because that provides definitely more information and chances of missing out anything is less. So you gradually can change your discomfort. So another example, suppose you have a longitudinal bipolar montage here. You can easily see that there is a right temporal, there are some spike wave or some fast activity. It is in the right temporal. Suppose you use now A2 montage or A2 electrode as a reference. So what has happened that because it is near to the right temporal, A2 has become active. So you still see some activity in the, probably here in the right temporal, this is activity, but because reference has become contaminated, the reference is also negative, so all the other channels also will become active. And that is why now it is in this page, it is difficult to localize where is the activity. While in this page, you can easily localize that it is on the right temporal. So that is how you try to use different montages in common average also has a problem. Suppose one of the electrode which I have used in the common is defective like that. So because electrode has a huge potential, so when you take the mean, it will not be 0. And that is why when you see probably one of the electrode has a deflection, whole of the common average will show this problem. You can simply overcome by you remove that electrode from the calculation of the average, and then you can be easily go with the common average. Why I told you common average is difficult. This is anybody looking at this bipolar montage will easily show that these are the vertex wave which are seen in the commonly in the central area. But the same thing if you see in the referential montage, now it is a bit difficult to really appreciate where these vertex waves are there. And this is the same page in the average montage. If you are experienced, you will be able to see that this is C3 and CZ, so these are the vertex waves. But because reference has become contaminated, there are other, because other waveforms or other electrodes are also showing these signals or waveforms. So that is why sometimes it's difficult to see in the average montage. It requires a bit of experience when you graduate from the bipolar to referential montage. Certain situation we need a special electrode, especially in cases of temporal lobe epilepsy, because temporal dipoles are located here where you do not have a particular electrode to pick that up. So that is why this Silverman electrode has been developed. You draw a line from the outer canthus of the eye to the tragus, and 2 centimeter and 1/3 from distance here you put this electrode. So these are T1 and T2 electrode, and these electrodes are very commonly used or routinely used during the pre-surgical evaluation. In the cases of epilepsy or in the routine scalp EEG, it may not be necessary. But for MAP, these are non-invasive electrode. You have to put one additional electrode. So it's always good to use these electrodes. In the rare pre-surgical evaluation, especially in the pre-MRI era, sphenoidal electrodes were used, where you put this invasive procedure, semi-invasive, through a needle. We put the electrode through the zygomatic arch. It is not for the routine scalp recording, only for the selected cases of pre-surgical evaluation, where you see this in the scalp, there is no spike, but because it is near to the source, sphenoidal electrode will show the spikes. So in selected cases of patient undergoing pre-surgical evaluation, it is used, but it is not for the routine scalp EEG recording. Coming to some other technical aspect, impedance is very important. Impedance is the resistance between the electrode and the surface. So more the resistant, you will lose the signal. Less the resistant, you will pick up the extra activity. So your impedance should be adequate, and that is why it should be kept less than 5 kilo ohms. And whenever EEG technician does the first page, you will see, so this is, you can set the what time level of impedance you want. When all these channels are showing green signal, that means that electrode is properly placed. So if there is anyone is showing some red, that means that that electrode is loose and you need to recheck that electrode. So that is technician does it, and this is how it will look like. What is this red and green signal? And there is so in this case, this has a low impedance, and that is why it is picking up these external artifacts. Calibration and the EEG, that is also one thing which was more useful in the cases of the analog EEG, but in the digital EEG, this is the first page you will look like. So this is the calibration page. Calibration is to ensure that all of the input and amplifier is working normally. Okay? So in this amplifier, you have a different input. So if each of the input, if you put a same amount of the current, let us say 10 microvolt, the output from that particular electrode should be same in all the channels, isn't it? So if one of the output from the one of the channels is different, then you know that that particular input is not working properly and you need correction. That was a major problem in the analog EEG. Nowadays, this is not a major problem in the digital EEG. So, but this is the first page, which will look like this is the mechanical calibration. And you see all these channels in reference, you see this all waveforms are similar. So that means that your whole assembly of electrodes and amplifier is working normally. That is how you calibrate the EEG machine. Sensitivity is the one setting which you can adjust in the digital machine. It is just like you adjust the volume of your radio or your TV, so that comfortable volume you can hear. Similarly, we can change the sensitivity of the EEG so that you can look it carefully. Sensitivity is measured either in microvolt per millimeter or millivolt per centimeter. So we have to be careful, different machine uses this. So you might have a sensitivity of 7 microvolt per millimeter, but it may be a 70 microvolt per centimeter also. So that we have to be careful. And obviously, 7 microvolt per millimeter means that 1 millimeter contains 7 microvolt. 10 microvolt per millimeter means that 1 millimeter contains 10 microvolt. So the 10 microvolt per millimeter, although when you change the setting, your amplitude in the EEG will decrease, but the overall amplitude of EEG is more because 1 millimeter is now 10 microvolt. So that is why you try to reduce that amplitude and look it carefully, which we can set. So this we can change in the digital CA. EEG frequencies are waveforms per second, and these are the common waveforms which you see in the normal EEG. which we'll discuss. Normal activity in awake adult is alpha activity. Then you have slower theta and delta activity or faster beta activity, which will be discussed in this. Another important concept is filter in the EEG. So we have, as I told you, hardware filter within the EEG machine where the activity is filtered. But now in the digital machine, we have a digital filters. So still the activity can be filtered out and we can remove the unwanted activity. Okay, so there are three types of filter. High frequency filter, simply that it filters the high activity which is beyond one particular frequency. So that you have a 70 hertz high frequency filter means activity beyond 70 hertz will be filtered. Low frequency filter means activity below that particular frequency will be filtered. And notch filter is a narrow band filter, 50 hertz. So only the activity of 50 hertz will be filtered. So we have electrical activity as a 50 hertz. So we want to filter that 50 hertz activity. So we have this notch filter. USA, because they have a 60 hertz frequency, so notch filter is set at 60 hertz. So that is to remove that external. To give you this example how this filter and how we should not use the filter. So this is the page. If you see, you can probably will think that there are multiple spikes and almost like a periodic discharges in the bitemporal lobe, isn't it? Everybody will think like that. But this is the high frequency filter is set at the 15 hertz. And this is the original EEG frequency of 70 hertz. So these are the chewing artifacts, and this high frequency activity has been filtered out, and that is why it looks like this. Okay, so EEG looks very smooth, but it maybe leads to erroneous diagnosis of spike wave discharges. So another example here, it looks like that there may be a sharp spikes in the frontal area. This is a frequency filter of 15 hertz, but when it is a high frequency of 70 hertz, we know these are myogenic artifacts. And that is why majority of the time what you see, the EEG coming from the outside have a frequency setting of, filter setting of 5 to 15 hertz. So your EEG looks very smooth, but all the activity is lost and you can lead to a erroneous diagnosis of this kind of spike wave discharge. So do not use filter, keep your filter as open as possible from the 1 hertz to the 70 hertz. In very rare situation, you try to use the filters. So filters should be kept as open as possible when you read and write the EEG. So this was the real example. Initially, when we saw this EEG in the morning, in the video EEG, it looked like there is a electrographic seizure in the right temporal area and spike wave discharge. But actually, this patient has a lot of this artifact and frequency filter at 70 hertz. So, and this was all artifacts and no activity. So that is the importance of using filters. Similarly, for the low frequency filter, we can easily make out that there is a profound slowing on the slow waves on the right temporal region along with this slow or sharp wave discharges. This is a low frequency filter is 1 hertz, 0.1. Now low frequency filter of 5 hertz. So activity below 5 hertz has been cut off. So you have a slow activity has gone, and now it is very difficult to really recognize their spike and this. So this is the importance of filter, and you know the filter, but don't use the filter while you read and do the EEG. So that is the important thing which we need to understand. Paper speed in the previous era, how many millimeter paper is passing every second. So standard was 30 millimeter per second. So in paper EEG, every second this page will move by 30 millimeter. In the digital now we have around 10 seconds per page. So 10 seconds per screen page is there. So suppose this is only used usually when you want to see the periodic complexes so that they are coming rhythmically and regularly. So you compress the EEG, you have 20 or 30 seconds in a page, and then you can see that these are the periodic discharges. So this page speed is also important, and some of the machine when you may not be able to see EEG waveforms may look deformed if this page speed is not taken care of properly. So this is how we come to the technical aspect. This is the standard way of examining the EEG, and this we will learn through the workshop. Initially, always go for the background activity. Background activity is whether normal and whether there is in a focal or generalized slowing. And so this is the only first thing is to look for the background and slowing. And second in the EEG is to look for the transient or any paroxysmal waveforms. And as we'll see, there are only 3 differential diagnoses. EEG is very simple. Look for the background and look for the paroxysmal activity. And you have to only differentiate this paroxysmal activity is normal, whether it's an artifact or whether it's a spike. So only 3 differential diagnoses, isn't it? So in neurology, patient comes with developmental delay, you have 50 differential diagnoses. You have to choose 1 out of 3. So that is how the EEG is very simple, and that is what we are trying to make in next hours. Now, in the next 5 minutes about the localization principle, how we localize the waveforms and the EEG. So as I told you, there are always have to be 2 input because we have to have a differential amplifier. So just remember one way, if input 1 out of this, in any channel, 2 input, channel is the difference of between these 2 input, okay? So if input 1 is negative, the waveform in that channel will be upward deflection. That is only. Input 1 negative, and negative is up in the EEG. Input 1 negative, that will produce a upward deflection, okay? And this is all relative to the input 2, so not the absolute. To give you some example, suppose let us see how we localize in bipolar montage. This is probably how we try to localize the spike. Let us say C4 has a potential of -70. There is a spike or a negative potential of -70 underlying C4. So what will happen there, let us say concentrate on this F4 C4 channel. So C4 is negative, F4 is relatively positive, isn't it? So input 1 positive, that means it will produce a downward deflection. Negative upward, positive will be downward. So in F4 C4, there will be a downward deflection. What will happen in the C4 P4 channel? Because C4 is negative as compared to P4, because C4 negatives, input 1 is negative, it will produce a upward deflection, okay? So in this adjacent channel, F4 and C4, here is a downward deflection, here is a upward deflection. There is a positive polarity, negative polarity, positive phase, negative phase. So in these nearby channels, there is a reversal of the phase from the positive to negative, and that is known as the phase reversal, okay? So phase reversal, you see, it is not like it is absolute potential or negativity here, but because of these electrodes are placed in a particular manner, so because if there is a negativity in one particular electrode, the 2 adjacent channel will show this reversal of the phase, and it is reversing across these 2 channels. Common electrode is C4, so we know that maximum potential is C4, okay? So that is we try to localize in bipolar montage through the help of this phase reversal. But that is, common scenario will be like this. There is no one electrode, the first time I've told, no one, if activity in one electrode has to be an artifact. So this is a common scenario. This is also physiological field. C4 has a potential of -70. So nearby electrode has a lesser potential. P4 also has a lesser potential. So now what will happen in Fe to F4? Because F4 is negative, Fe4 is not, Fe2 is not involved, so it's positive. So there is a downward deflection. Here F4, C4, both are negative. But C4 is more negative as compared to F4. So F4 is relatively positive. So this again will be downward deflection. C4, P4, because C4 is more negative than P4, that is upward deflection. So you have a complex field, but again phase reversal is across C4, so we know that maximum potential is C4. That is the phase reversal we try to understand through localization in bipolar montage. Referential montage, it's easy to localize because, here A2 is 0. So whenever in anywhere you subtract 0, C4, so maximum activity is obviously in the C4 because it is a potential of -70. Other electrode will show a lesser potential. So it is amplitude of the activity or amplitude of the spike. Highest amplitude will be the localization. So that is easy to localize in cases of referential montage. But sometimes phase reversal can happen in the referential montage, and except barring some situation, it is usually non-physiological. Suppose you have a temporal spike T4 potential of -70, but T4 is spread to the A2 also. So A2 also becomes negative, and that is the contamination of the reference. So now what happens that A2 is negative. So in all other channel, Fe2, because it is positive as compared to A2, F8 is also positive. So you see the potential is only in the T4, but all other channels are going a downward deflection. So in common average, if you see 1 or 2 negative, but all the channels are showing a positive deflection, it is likely that it is a contamination of the reference. You get a phase reversal here, but that is a technical phase reversal and not a real phase reversal. So that situation will indicate there is a contamination of reference. Certain situation, there may not be phase reversal in bipolar montage. It happens only when your electrode, like let's see, there is a potential of minus 70 in O2. So because P4O2 will show a downward deflection because O2 is negative, but you don't have any electrode beyond that, so you cannot demonstrate there is no phase reversal here. So in situation where the electrode is either in the beginning of the chain or in the end of the chain, that is the end of chain phenomenon, we sometimes will not able to see a phase reversal in bipolar montage. People have developed different method. You can connect O1 and O2 and can demonstrate the phase reversal. Majority of time by visual inspection or looking into the common average montage, we will be able to see. Because here whether this is an artifact because it's only one electrode is involved. So that also we need to. So with experience, we'll be able to see that. So these are the examples of this. Anyone where this will be spike? This is a bipolar montage. And this is going down, this is going up. So phase reversal is happening across T1 and T2 and T4. T2, T4 is not showing any activity. That means what? So both T2 and T4 have the same activity, isoelectrical. So the negativity is maximum in the T2 and T4. So that the source is T1 and T2 anterior temporal and phase reversal is happening at this point. Same example here, phase reversal is happening at F8. You can easily see in the referential montage, highest amplitude in F8. So we try to localize. I'm finishing in 5 minutes. Thank you very much for your attention. How we try to localize this way. So these are the principles, and this is what we'll be practicing in next few sessions. Thank you.